My name's Darren Holmes, and continuing on in the book Get Started with MicroPython on the Raspberry Pi Pico, we're going to investigate Chapter 8. In Chapter 8, we're going to be using the Raspberry Pi Pico's built-in A to D converter. So up until now, we've been using digital inputs where they've been on or off or 0 or 1. We've been using a push-button switch, and we've been using LEDs. We used a passive infrared sensor to detect motion, and all it did was send us back a 0 or 1. So today what we're going to use is the analog input. So today we're going to be using a 10k ohm potentiometer as a voltage divider so that we can input a signal between 0 volts and the Raspberry Pi Pico's 3.3 volts. Page 93 of the book talks about the analog to digital converter. So I would like you to read this over a few times until you understand it. I'm going to give you the shortened version now. The first thing to note is the A to D converter is built into the RP2040. So the next thing to note is the ADC, or the analog to digital converter, has two key features. The first one is resolution, and that's measured in digital bits. And the second is channels, or how many analog signals it can accept. So the A to D converter on our Pico has a resolution of 12 bits. So what this means is it can accept an analog signal in and it converts it to a 12-bit digital signal. So that means it converts your analog signal into a number from 0 to 4095, and I'll show you where that comes from in a moment. It says that this is handled in MicroPython, and it's transformed into a 16-bit number ranging from 0 to 65,535. And then it says that we have 3 channels brought out on the GPIO pins. So that's 26, 27, and 28. And it says there's also a 4th channel, which is connected to a temperature sensor built into the RP2040. So going to the back of the book and looking at Appendix B, you can see in the little guide down here, ADC channels are in the dark green. So here we can see we have ADC 0, ADC 1, a separate analog ground for reference, and ADC 2, and we can also use a voltage reference instead of the 3.3 volts that's powering our Raspberry Pi Pico. So in the RP2040 datasheet, under section 4.9, it talks about ADC and temperature sensor. So it says the RP2040 has an internal analog digital converter, ADC, and it has the following features. You'll notice it's a 12-bit. It's also a 5-input MUX. 4 inputs are available on package pins, and 1 input is dedicated to the internal temperature sensor. So here you can see each of the analog inputs. So we have it on 26, 27, 28, and 29, and the temperature sensor, and they're all multiplexed to a single ADC converter. So the ADC converter can only convert 1 channel at a time. So in figure 115, they've got a block diagram of the circuit, and you can see that we have the 5 analog inputs that go into a sample and hold circuit that is compared to a digital to analog converter. So it's a little bit complex for what we need to know, but I did want to show you the block diagram and the fact that there is 5 inputs but only 1 converter in the RP2040. So I've just seen from the data sheet that we have 5 analog signals, so let's see if we can account for all of them. So pin 31 on our schematic of the Raspberry Pi Pico comes out to ADC 0. Pin 32 is ADC 1. And it looks like pin 34 is ADC 2. So when we look at the RP2040 on our schematic, you can see there's ADC 0, 1, 2, and 3. And don't forget there's a temperature sensor built into the IC itself, which we cannot see here. So let's see if we can find ADC 3 somewhere on the schematic. So you can see in the bottom right-hand corner, we're using GPIO 29 ADC 3 to monitor some kind of voltage level. We have a FET, a field effect transistor, being controlled from the 3.3 volt supply, and it looks like it's monitoring a voltage divider, looking at the system voltage coming in, which is approximately 5 volts from our USB. So that's where the extra ADC is being used by the Raspberry Pi Pico, so it's not available for us to use in any of our projects. So your book has a talking point here. It's Y65535. So if I have 1 bit, it can have a value of 0 or 1. Now if I have a second bit, it can have a value of 0, and the first bit can have a value of 0. My second bit can have a value of 0, and my first bit can have a value of 1. Then my second bit can have a value of 1, my first bit can have a value of 0, and my second bit can have a value of 1, and my first bit can have a value of 1. So you can see here, when I go from 1 bit to 2 bits, I've doubled the number of possible combinations available to me. So if I go to a third bit, it can have a value of 0, and then it can have a value of 1. So you can see I've now gone from 4 different combinations to 8 different combinations. There's a formula we can use to calculate these. The formula is 2 to the power of n, where n represents the number of bits. So if we have 2 bits, we have 2 to the power of 1, which is equal to 2. If we have 2 bits, it's 2 to the power of 2, which is equal to 4. And then if we have 2 to the power of 3, that is equal to 8. So you can see every time we add a bit, we double the number of possible combinations available to us. So if we take 2 and take it to the power of 12, because we have a 12-bit A to D converter built into our Raspberry Pi Pico, that gives us a total of 4,096. Now it says in the book, MicroPython will convert this to a 16-bit number. So that's 2 to the power of 16, and that's equal to 65,536. So you can see the maximum number is 65,535, but there's 65,536 total combinations because we have to add the number 0 in. So in the next section of the book, we're going to start reading the potentiometer values using our Pico. So figure 8-2 shows us how a potentiometer works. we can see it has 3 terminals. The center terminal always goes to the wiper arm. You can see the relationship of the resistance between the wiper arm and the first pin is going to be less than between the wiper arm and the last pin. So as you rotate the knob on the potentiometer, it's going to change the relationship of the resistance between the first pin and the wiper arm and the wiper arm and the last pin. Please note that the resistance between the first pin and the last pin is always the same. So if you have a 10K ohm potentiometer, measuring the resistance between the first pin and the last pin will always be 10K ohms, regardless of where you turn your knob on your potentiometer. Now figure 8.1 shows us wiring up a potentiometer with only 2 pins. When you wire it up with 2 pins, it's really a rheostat and it's used to limit current flow. So that will not give us a good reading on our Raspberry Pi Pico. So when you wire up your circuit, I want you to wire it up to figure 8-3. This is using a potentiometer as a voltage divider. You can see the 3.3 volts goes to one pin. The ground goes to the other outer pin, and the center wiper arm goes to the Raspberry Pi Pico. So when we adjust our potentiometer, the output voltage is going to be between the 3.3 volts and the ground. So this is wiring your potentiometer up as a voltage divider. Looking at Wikipedia, we can type in potentiometer and it gives us a picture of what an average potentiometer would look like. It tells us it's a 3-terminal resistor. If only 2 terminals are used, one end and the wiper arm, it acts as a variable resistor or rheostat. It shows us a little bit of the construction. So once again, you can see it's 3 terminals and the center terminal is connected to the wiper arm. It talks a little bit about resistance position relationship and the taper. So there's 2 kinds of tapers. There's linear, which means it goes from 0 to 10K in a linear fashion. So if you go halfway round with your potentiometer, it should be 5K ohms. The other taper is a logarithmic potentiometer. In this case, when you adjust it halfway, it will not be at 5K. It'll be closer to maybe only 100 ohms. It tells us the rheostat is basically used to adjust magnitude of current in a circuit by changing the length. It says in here, under applications, potentiometers are rarely used to directly control significant amounts of power. So here it talks about audio control, and they're using a logarithmic potentiometer. It is used as a volume control in audio power amplifiers. This is also referred to as an audio taper potentiometer, and that's because the amplitude response of the human ear is approximately logarithmic. So in your book, it does have a talking point about linear versus log, and it says if you find turning your potentiometers slowly between one limit and the other makes the numbers change very slowly at first and then starts changing more rapidly, then you know you have a logarithmic potentiometer. So our next step is going to be to write the code. So what we're going to do is import the machine library, import uTime, and then we have to set up a variable, and our variable, we're just going to call it potentiometer, is going to be equal to machine.adc. Now we haven't used .adc before, but what this does is it sets up the pin to be an analog pin. And we're going to be using GPIO 26. So keep in mind the variable potentiometer is actually an object. So our object points to the machine and it's an analog pin 26. So we're going to need to look that up on our appendix and find out what the physical pin is on the Pico for that. Now in our main code, we're going to run an endless loop. So we put in while true. And what we're going to do is we're going to print potentiometer.read underscore U16. So what this does is it brings in a 16-bit number, and that's going to be our analog to digital conversion. Then we're going to wait 2 seconds before we come up and print the next value. So this won't be continuously printing on our screen. It'll take a 2-second break in between prints. So checking out the reference in the back of the book, we can see that GP26 is going to be pin number 31 on our Raspberry Pi Pico board. So this is my circuit wired up. You can see I have the ground bus hooked up. I have my 3.3 volt power bus hooked up. Down here on my potentiometer, you can see I have power going to this end of my potentiometer, and I have ground going to the other end of my potentiometer, and out of the center, that's where the wiper goes, that goes to pin 31 on my Pico. So I just wanted to give you a close-up of the 3 pins on my potentiometer. And you'll notice the center pin is going to go to the green wire, and the pin on the right of the screen goes to the red wire, and the pin on the left of the screen goes to the black wire. So I'm going to start off my readings with the potentiometer, and it's going to be in the centered position. So you can see the little arrow on here is in the centered position. So it should read somewhere between 0 and 65,000. So halfway should be somewhere around 33,000. Please note the orientation of my potentiometer. The bottom edge is towards the bottom of my board. And in this position, when I turn the knob on my potentiometer fully counterclockwise, I should get my lowest reading, and when I rotate it fully clockwise, I should get my highest reading. So if you have a different style potentiometer, such as the one shown here, it still has 3 pins on it. The center pin is still the wiper pin, but the spacing is a little bit different from the small blue one that I just showed you. So you're going to need to space out your ground and your power 1 space further away from the center pin. And when you place it into your breadboard, we need to orient it so that the adjustment shaft is pointing down, and try to find a center position. So turning it fully counterclockwise versus turning it fully clockwise. So we can see about halfway should be about there. So you can see there's a little slot in there. So if you adjust it halfway, the slot should be horizontal to your board. So you can see I've entered my code into Thonny, and I've saved it as potentiometer.py. So I'm going to go ahead and run this. And you can see here that it is at approximately the center position, somewhere around 31,000. So I'm going to turn my potentiometer fully counterclockwise and just wait for it to kind of stabilize. So you can see it's somewhere around 128 to 140. So now I'm going to turn my potentiometer fully clockwise, and you can see my maximum number is 65,535. So you'll notice our book has a little talking point, and it says 0 is the hardest number. It says if you can't get your Pico's analog input to read exactly 0 or exactly 65,535, don't worry. And then it talks about all electronic components are built with a tolerance. So this means that we're not going to get exactly a 0 or 100%. So I wanted to dig a little bit deeper into this. So on the Raspberry Pi Pico datasheet, section 4.13 talks about using the ADC. And if you read through here, it says the ADC does not have an onboard reference and therefore uses its own power supply as a reference. It says this is a simple solution but does have the following drawbacks. Number one, we are relying on the 3.3 volts output accuracy, which isn't great. Point number two, we can only do so much filtering. And it says therefore the ADC will be somewhat noisy. Then the third point is the ADC draws current. So what they're saying is there is going to be inherent offset, and it's going to be approximately 30 millivolts. So that's probably why we can't get exactly 0. So the other question I had was, how exactly does MicroPython go about changing the 12-bit A to D conversion on the Pico to a 16-bit number? So I went out searching and I found the Raspberry Pi forums, and this particular topic, it says nowhere does it actually state what transform to a 16-bit number ranging from 0 to 65,000 actually means. So if we scroll down through some of these answers, they gave us a little illustration here. So here's our 12-bit number, and basically it says all it's doing is shifting those 12 bits down to the 16 bits. So all 12 bits get shifted into the most significant 12 bits of the 16-bit number that's returned. And then to fill in the bottom 4 bits, what they do is they take the top 4 bits and just shove them into the lower 4 bits. So this isn't going to end up with a very accurate number. So if you're going to be looking up further documentation in the MicroPython docs, our particular documentation is in section 9.11, and it refers specifically to the RP2040. So in here you can see we're going to be using ADC pin, and we're going to do a read underscore U16. So this kind of gives us the syntax that we're looking for that's specific to the RP2040. Remember, MicroPython was written for many embedded controllers, not just the RP2040. So looking further through the documentation, you can see there's an ADC class, and we have the ADC pin, the ADC read underscore U16, which is going to read in an analog value in the range of 0 to 65,535. But they also have an ADC.read underscore UV, which is read an analog value in millivolts. This does not work on the RP2040. You'll also note in here there's an ADC.read in brackets, and it says it reads the value on the analog pin and return it. The return value will be between 0 and 4095. This also does not work on the RP2040. The next section in our book is going to deal with converting our A to D number, which is 0 to 65,000, into a voltage. So to do that, we're going to need a conversion factor. So keep in mind that our maximum voltage is 3.3 volts, and we have a reading of 0 to 65,000. So if we create a conversion factor, and this is just a variable that's going to be equal to the 3.3 volts divided by the maximum reading that we can get from our A to D converter, which is 65,535. So then we're going to change our main loop in our program. So now instead of just printing our reading, what we're going to do is we're going to calculate the voltage. So the voltage is going to be equal to our 16-bit reading times our conversion factor. So when we're programming, we don't use a X as multiplication. We use a little asterisk, and the little asterisk indicates multiplication. So once we've got that value into our variable named voltage, we can then print voltage and then have a little sleep before we print the next number. So before we start modifying our code, we need to stop it from running. So once we've finished typing in our new code, we can come up and say File, Save, and then we can run our new code. So now you can see at the low end, we're getting somewhere around 4 millivolts. So I'm going to turn my potentiometer to approximately halfway, and you can see halfway is somewhere around 1.6 volts. Now I'm going to turn it fully clockwise, and you can see I'm getting the full 3.3 volts. The next section of the book deals with measuring temperatures, and it says your Raspberry Pi Pico's RP2040 microcontroller has an internal temperature sensor, which is read on the 4th analog to digital converter channel. So you can see in here they're giving us the same basic code, import machine, import utime, and now we're going to set up a new variable called sensor temperature, and it's equal to machine.adc4. So looking at the appendix in the back of the book, you can see on the right hand side here, this is the reference to our ADC channels. So we've got channel 0, 1, 2, but no mention of 3 and 4. So checking the Pico datasheet, we're going to reference the general purpose IOs in section 4.2, and we're looking for references to our GPIO pins. So GPIO 0 through to 22 are digital only, and GPIO 26 to 28 are able to be used either as digital or analog, and they're software selectable. There's a little thing to note here. That's when we're using ADC capable pins. They have an internal reverse diode to the 3.3 volt rail. So the input voltage must not exceed this 3.3 volts by more than 300 millivolts, or we're going to damage our Pico. It also says if the RP2040 is unpowered, applying voltage to these pins will leak through the diode into the 3.3 volt rail. So this could also have some damaging effects on our Raspberry Pi Pico. So checking the schematic out, we can see the RP2040 has ADC channel 0, 1, 2, and 3. And we just saw that 0, 1, and 2 were brought out on the output pins. And I've mentioned before ADC3 comes down here, and it's actually looking at the voltage divider voltage. So what we're looking at here is the input voltage. So this is the 5 volts from our USB. And it's 200K and 100K. So the voltage it's looking at there is 100 divided by 300K times the 5 volts. So that's going to work out to about 1.66 volts. Now you'll notice the FET stops leakage through ADC3 pin diode into the 3.3 volt net when the 3.3 volt supply is off. So this FET here only allows current to pass through it when we have 3.3 volts. So this ADC pin is not going to be looking at the 5 volts if the chip is not powered. And then finally coming over to the RP2040 datasheet, you can see section 4.9.5 deals with the temperature sensor, and it says the temperature sensor measures the voltage of a bias bipole diode connected to the 5th ADC channel, and it's labeled AINSEL4. So that's where that 4 comes from. So now we know where the 4 comes from. So we're still going to use the same conversion factor we used before, and this converts our analog reading from a digital number 0 through 65,000 into a voltage. So the next thing we need to do is actually convert this voltage into a temperature reading. So what we're going to end up doing is, in our while true loop, our reading is going to be equal to the sensor temperature reading, and it's going to be a 16-bit number, times the conversion factor. So now our reading becomes a voltage. And in order to convert it to a temperature, we're going to use this calculation. So it's 27 minus our voltage conversion reading minus 0.706 divided by this number. So where does that number come from? So coming back to our RP2040 datasheet, still in section 4.9.5, temperature sensor, it says the temperature can be approximated as follows, and here's the formula that we're using, so this is where all those numbers have come from. So then finally, to finish the loop, we're going to print out the temperature, and then we're going to wait 2 seconds before we do the conversion again. So they give us what the final code should look like that we are going to type into Thonny, and we should save it as temperature.py. So I've typed my code into Thonny as shown in the book, and I've saved it as temperature.py. So now I'm going to go ahead and run it. And it might take a few seconds to get the kind of approximate room temperature. So you can see I'm around 22.36 degrees. My thermostat says it's about 20 degrees. So obviously this is in Celsius. So one thing that you can do is you can put your finger, make sure your finger's warm, so you might want to rub your fingers together and then touch that big square chip in the middle of your Pico. That is the RP2040, and you can see my finger was a little bit cold, so it actually cooled it off a little bit. So I have with me a can of Super Cold. This is where I got it from on Abra's website. It's about $20 a can, so it's not cheap. And it will cool a circuit down to about minus 51 degrees Celsius. So what I'm going to do is I'm going to spray the large black chip with my Super Cold. And you notice the readings drop quite dramatically. You don't need to squirt a lot on there, just a little squirt, and then slowly your IC will warm back up to room temperature. So this is kind of a cool feature of the RP2040, the built-in temperature sensor. It's not going to be extremely accurate, and remember, the more code that you're running on your Raspberry Pi Pico, the warmer that IC is going to be, so it's actually going to end up being warmer than room temperature. So before we finish up our discussion on analog to digital conversion, I just want to bring you back to figure 115, where I said that we can have a possibility of 5 different analog inputs, but we only have one digital to analog converter. So I have this question that is, if I have one digital to analog conversion, and I want to do several conversions, how long do I have to wait before I can do the next conversion? So it says in here the ADC requires a 48 megahertz clock, which is what we're running on the Pico. And it says capturing a sample takes 96 clock cycles. So 96 clock cycles times the period, and the period is 1 over 48 megahertz, comes out to 2 microseconds per sample. So you can see we can take multiple samples, but we need at least 2 microseconds between them. So in the final section of the book, we're going to be fading an LED with pulse width modulation. So your Raspberry Pi Pico can take an analog signal in and convert it to a digital signal, but it has a real hard time trying to take a digital signal and trying to convert it to an analog signal. So there's a way to fake an analog signal, and it uses something called pulse width modulation. So I'm going to give you a little review of what pulse width modulation is. So to describe pulse width modulation, I'm showing you a typical digital signal. It goes between 0 and 3.3 volts because that's what our Pico does. What happens is the waveform is high for a period of time and then it's low for a period of time. So duty cycle is the time high divided by the period, and the period is the time high plus the time low, and we multiply that by 100%. So if 50% of the time it's high and 50% of the time it's low, so this ends up being a 50% duty cycle. So what is the average voltage that's output here? So because it's 50% of the time, we can take a look at what's halfway. So halfway between 0 and 3.3 volts is somewhere around 1.66 volts. So our average voltage for this waveform is going to be about 1.66 volts. Now the thing is, the frequency of this waveform has to be such that during the time high, the LED is not on, and during the time low, the LED is off. So if we were to run this at about 10 Hertz, we would see the light blinking on and off at approximately 10 times per second. So in order to stop it from blinking, we have to run the waveform faster than our eyes can see this blinking. So if we run this thing at about 1000 Hertz, it's going to run faster than our eyes can see it blinking on and off. So it's going to look like it's about half brightness. So in the next line, you can see I've reduced the amount that my time is high. So I've reduced it to about 1/3 of the period. So if the time is high for 1/3 of the time, I've got a 33% duty cycle. So 33% of 3.3 volts is approximately 1 volt average. Now in the last example, I've increased my duty cycle to 67%, so the time is high for 2/3 of the time and it's low for 1/3 of the time. So 67% of 3.3 volts gives me an average of 2 volts. So you can see by changing the duty cycle, I changed the average voltage going to my LED. So in the last example, you can see my time is high 100% of the time. The signal never goes low. So my duty cycle is 100% and the voltage is going to be 3.3 volts. So this is going to be my brightest setting. So the book has a talking point here about pulse width modulation conflicts. So on the next page, they're giving us the pinouts for pulse width modulation. So you can see the orange labels on the side of all these pins indicate that's where pulse width modulation is available. So you can see it's available on every single pin. Now in here we also have a letter and a number. So you can see that GPIO pin 0 or pin 1 on our Pico is labeled A0. If you look at pin 21, which is GPIO 16, it's also labeled A0. So we can't be using pulse width modulation on these two pins at the same time, because every time we change the duty cycle, we're going to change the duty cycle on both pins. So looking at the data sheet for the RP2040, section 4.51 has an overview of pulse width modulation. Now it says the pulse width modulation block has 8 identical slices. and each slice can drive 2 pulse width modulation output signals. So this gives us a total of 16 controllable pulse width modulation outputs. However, all 30 GPIO pins can be driven by the pulse width modulation block. So you can see here the numbers represent 0, 1, 2, 3, 4, 5, 6, 7. So that's 0 through 8 slices. And then each slice can drive 2 channels. So we have an A channel and a B channel. A channel, B channel for slice 1, A channel, B channel for slice 2. So that's what they're talking about when they say pulse width modulation conflicts. So figure 8-5 in the book says we're going to add an LED. So what we're going to do is write some code that takes the input from the potentiometer and outputs it to the LED, making it brighter and dimmer. So the book gives us a few lines of code that we need to add to our program. The first one is we're going to create a variable called LED, and it's going to be part of the machine library, so it's going to be an object, and it's going to be pulse width modulation. And it says machine pin 15, so that's GPIO pin 15. So GPIO 15 is actually physical pin 20 on our Pico board. The next thing we have to do is set up the frequency, and remember in my little tutorial I said we can't run it at about 20 Hertz because we'll see it blinking. So here they're setting the LED frequency to 1 kilohertz. Now we have to go into our program and delete the print voltage and U times sleep 2 seconds, because what this will do is give us a delay between changing the potentiometer and what comes out on our LED. But we also need to add this particular line, and this sets up the duty cycle. So you can see LED.duty_16 means we're going to be sending a 16-bit piece of data to the LED's duty cycle. And that data is going to come from our potentiometer doing a 16-bit read. So then they show us what our finished code should look like in Thonny. So I've typed my code into Thonny. I've called it pwmled.py. So I'm going to go ahead and run this, and I'll show it to you on my breadboard. So here's my circuit on the breadboard. You can see pin 20 goes to my 330 ohm resistor that goes to the long leg of the LED. The short leg of the LED goes up here to my common or ground bus. I have my potentiometer, and the first pin is going to get grounded. The last pin goes to 3.3 volts, and it's hard to see here, but the center pin comes all the way over here to my Pico. So right now I have it fairly centered, so the LED should be about half brightness. So if I turn my potentiometer counterclockwise, it should slowly get dimmer until it goes off. So right now you can see the LED looks like it's off. So if I turn my potentiometer clockwise, it should slowly get brighter and brighter. So there's half brightness. And then when I get fully clockwise, it's as bright as the LED will go. So this concludes the video on Chapter 8. We covered a lot of material in here. We did some A analog to D digital conversions, and we took a look at the RP2040 built-in temperature sensor, and we did some pulse width modulation. We also hooked up a potentiometer. So we covered quite a bit of detail in there so that you knew some of the background and where it came from. So it looked like an easy chapter, but we had to dig a little bit further. Now in my next video we're going to be taking a look at a data logger. Basically what we're going to be doing is taking our Pico, we're going to power it up externally, and what we're going to do is we're going to capture some temperature readings and store them in a file. So it should be really interesting. So I want to thank you for watching. Please don't forget to subscribe, turn on notifications, and hope to see you on my next video.